Linda Stevenson met Ed when both were in graduate school. Linda is now an editor and science writer.
We used to go out to eat a lot, go to a favorite restaurant called Portobello.
Oh, that's right.
And it was a highlight of the week to go out to dinner there. But they had paper napkins, and Ed was always grabbing a napkin and writing an equation on it. So I tried to find different restaurants that had cloth napkins so he wouldn't be writing equations all the time during dinner. Didn't really help very much.
Well, Chuck was beam physicist.
Unlike Linda, Dorothy knew nothing about physics when she married Chuck.
Got a call in the middle of the night, and I could tell from his side of the conversation that it was the lab. And when he got off the phone, he said he had to go in and fix something, that something was wrong. I said it sounded like it was the polarity was reversed on the steering magnets. He laughed, went off to the lab, walks into the control room, tells them, "Ha ha, my wife says it's the polarity reversed on the steering magnets." He said, "We didn't check that." They went and checked it, and that's what it was. So I don't even have to go in to fix the machine.
That's right.
"2 a.m. Jim begins another shift on duty.
One thing that happens late at night is it seems your body temperature drops and you start to get cold. It seems the best way to keep going at night is to eat a lot of sugar and drink things that have caffeine in them. We often sometimes crawl up close to the electronic crates that blow out a lot of warm air, too. That keeps you warm. A big part of what happens during an experiment is just keeping everything working. There's always something breaking down, something to be fixed.
Well, as you can see, the beam is off and something is beeping. So I can go to the limits page and find out what it is that's going off. And this says, as you can see, that the main RF has faulted off. I can look on this page and I can see that indeed it has faulted off, and I will now have to go upstairs and fix it.
Although she had once planned to be an experimenter, Denise has altered her plans.
I guess I'm an operator instead of an experimenter because I wasn't interested enough in physics to continue my education. I had gotten my BS in physics, and I had applied to the graduate school because I thought I wanted to go, but then I decided not to. After seeing all the hard work Carl had to go through, I decided I wasn't that dedicated to it.
Denise loves belly dancing as a hobby, but her future still lies in science.
After being out for 4 years and working on the backside of physics, I've decided that I'd like to go back and get a degree in engineering, and I'll be working on it part-time while Carl's still in school. When he graduates and gets a job someplace, I'll go back to school full-time and hopefully get a master's or a PhD in engineering.
Hey, Carl?
Yeah.
11 a.m.
You know what would be fun to do?
With half the data collected, a disagreement comes up about how to proceed.
No, I was just thinking, as long as we're back here at large angles, it looks from this data that we already have as if the J dependence is going away. I wonder if it reappears someplace else, like in the tension.
Because the experiment now seems to be going well and no further problems are expected, Ed wants to expand the data taking beyond the original proposal.
Well, the only problem with that, Ed, is it's going to take hours to do any point if we go to the tensor analyzing powers.
Yeah, I know.
And how big's the cross-section back here?
Well, I think both of us have different expectations about what we want to get out of it. And Carl was taking a very conservative approach, and I was taking a more liberal approach. I wanted to look a little bit more ahead at what we were doing, and Carl wanted to make sure that we got done what we set out to do. Well, it's small, I know that, and the things are going to be hard to measure because of this 1/2 factor in front. But I'd still like to see what it looks like, even with...
Well, every experiment has a spokesman, but if people on the experiment think that something's not being done right, they'll come out and say it. I mean, none of us are shrinking violets when it comes to whether or not we believe something is being done right. Experiment.
Sure it does.
Look, let's finish off.
Let's show back one data point out here and say, look, there might be this interesting effect if we only understood it a little bit better.
Let's finish what we know we're doing. I mean, we're not running that much ahead of schedule. Let's finish off. And it's full contact physics out there, and that's the way that the entire field is, and that's how we make progress. by continuously challenging one another to go beyond what's been done before.
No, I think we ought to do it now. I want to take a look.
Well, you're the spokesman on this, and it's your neck, so to speak.
Yeah, I guess it's my neck. Okay.
This argument has importance beyond this experiment. Because there are many requests to do experiments, a Program Advisory Committee, or PAC, decides which experiments and which experimenters will get beam time on the cyclotron.
Well, you have to get up before the PAC committee and justify your idea to them if you want to do an experiment out there. And it's very trying because you get up there and you try to convince these people that, in the first place, what you're doing is worth doing, that it's good stuff, and in the second place, that you're capable of carrying it out. And people can get very savagely treated. They can be humiliated even by this committee if the committee feels that what they're doing is not useful. I mean, I've heard comments like, lead-off response will be, "This is kiddie physics. You ought not to be wasting your time doing this sort of thing." And it's all too easy to go crashing in flames before this committee. But that's the way that they try to make sure that only good work gets supported. You have to get up there and you have to convince this body of wise men that you know what you're doing and that it's worth carrying out.
Sunday afternoon. The run continues smoothly as Chuck collects the additional data Ed requested.
Man is characterized of all the creatures as mating himself to his environment by being a tool maker. His very clothes are tools for purposes. And perhaps in things like the spacecraft or a cyclotron, man carries his tool-making abilities and drive to an extreme. So now if you want to ask the question why in terms of specifically a cyclotron, that comes because we need to understand as humans more about these things that make us up, the atoms and the nuclei of the atoms and these esoteric forces.
Chuck Foster also worked with these researchers at the old IU cyclotron. Built during World War II, it operated until the late 1960s, when its primitive design and low energy beam made it obsolete. The design for the new cyclotron called for 4 magnets instead of 1, a controversial idea.
Really, it's been more of a success story than was originally thought. When it was first designed back in the mid-60s, a lot of the people in the field, a lot of the experts thought that this machine could not possibly work as advertised, and they stood up at meetings and they said so. There were a couple of things that were new. One was the sector focusing design, where you've got the 4 big magnets up on jacks. And the problem there is that you've got to keep those magnets aligned relative to one another to within a couple of thousandths of an inch. In addition, nobody, to the best of my knowledge, had ever tried to run 2 cyclotrons back to back. You get into problems matching the output of one to the input of the other. You put all this together, and it just looked like a good idea that just couldn't possibly work. It worked out that this machine works spectacularly. It's one of the best cyclotrons in the world, excellent energy resolution, excellent variable energy, multiple beams. It's being copied everywhere from Holland to China now.
The new cyclotron was built in the rolling hills of southern Indiana. Bill Lazowski finds the surroundings a welcome relief from his work.
That represents the elements, and this represents the elements. But that's so high-tech that I need this to balance that aspect in my life. And I enjoy the drive in and drive out. It's a good time for me to put myself together for work or take myself apart to be at home. I wouldn't want to live any closer. I know that a lot of people at the cyclotron are interested in nature.
I don't know whether you noticed, but if you look at the azalea, there's a marking which is on the upper part of the flower that resembles the shadow of the pestle of the flower. When I was a poet, that brought all sorts of images to my mind about life and shadows in the wrong places and second existences and all sorts of things of that. But after I became really involved in physics, I didn't see things that way anymore. I saw them in terms of reproducible mechanical systems or mathematical equations or some such thing. And since that time, I've never written another poem. It just seems that there's two different ways of looking at the world. I ended up a physicist to a certain extent because it was an intellectual challenge. It means that when I was in school, I took an introductory physics course, and I found that it was the hardest course I had. And being somewhat stubborn, I took another physics course and another physics course and another physics course. It ended up that that's where my only 3 C's were.
Dorothy Foster once helped out on an experiment when a blizzard prevented other researchers from getting to the cyclotron.
One of the interesting things about that evening when I was taking data was, even though I didn't know anything about the physics and didn't understand what I was doing and knew very little about computers, the data comes in and a bunch of lines appearing as counts come up and a graph appears before your eyes. And I would catch myself watching things, and one time I can remember distinctly turning to Chuck and saying, "Hey, look, this is different." And I got excited like I really understood it. And you can get wrapped up into it, and you don't even realize it, but it's very addictive. And I can now understand why they'll go and get excited about seeing a bunch of little dots on a screen.
Physics is hard. It takes a lot of work. It involves a lot of dedication and long hours of work. He's at the cyclotron probably 90% of the time.
When Carl can get away from the cyclotron, he heads for the outdoors. Once away, Carl likes to get into things, like caves.
Well, caving is a lot like nuclear physics in that both really are dirty, nasty jobs, and nobody in their right mind would consider going out and doing it. But both are a challenge, really, and that's the way that I tend to view them. That there's not, it's something that demands a certain, say, mental toughness to go off in some hole in the ground and go in at one hole and come out in another, or to go sit out there midnight after midnight at the cyclotron watching data come in on your thesis, when it's certainly there are much easier ways to earn a living or to have a good time. And both very, it's a challenge in both. You can just live your life just sort of sitting around doing nothing, or you can go out and do things that force you to grow both mentally and physically.
"2 a.m. The final day of the experiment. Carl adjusts the spectrometer angle.
Oh, hell.
What Carl feared most has happened. A vacuum leak in the scattering chamber. Chuck is called in to help.
Chuck, this is beginning to tighten up pretty good.
Bellows feels all right. Feels like the band's tracking okay.
We've got about 1/4 of an inch to go. It should seal just fine.
Without a sufficient vacuum, the beam cannot travel to the target. The leak itself is quickly repaired, but it will take 4 hours for the vacuum to recover inside the scattering chamber. 4 hours of lost time.
Frustrations of being a physicist's wife are probably no different than being somebody else's wife who's dedicated to the job. I can remember I used to be really angry with him when he would be on call and the lab would not have called, but he would feel compelled to call the lab. And of course there would be some reason he would have to go in then.
I go to bed at night a lot alone. He's often not here. Sometimes he comes in at 3, 4, 6 a.m. One morning, when we woke up, I had expected him to come home sometime during the night. I wasn't sure when. So when I woke up, Alan came running into the room, and I said, "Shh, don't wake your father." I got up very quietly. We were tiptoeing around, and I turned around and looked, and Ed wasn't there. He had never come home.
I don't think I'd want him to be doing anything else because he is happy. Even though he does work real hard, I don't think he would be happy if he wasn't working hard.
Oh, I don't know about that. I can be quite happy when I'm lazy.
He doesn't know how to be lazy.
8 a.m. The beam has been back on target for only 2 hours. The experiment comes to a close as the team meets for the last time.
See if we can get an extension or just give up the beam after this.
Oh, I think...
Oh, there's Ed. Here comes Ed now.
How you guys doing?
Oh, we've been rescuing you
Rescuing me.
from the ill-fated after effects of your decision to go after tensor analyzing powers.
I see.
Ed, we had a
vacuum
vacuum
failure
failure last night.
So we lost 4 hours, and, okay.
We managed to
Bottom
get
line
most of the
is,
data, but
we didn't get all the points you wanted. We quit taking tensor analyzing powers, and we skipped every other point. We've come back, gotten a couple of the other ones. We got all the way out in angle, but we don't have as many points as you wanted.
So what's the step size and angle? Every 10 degrees?
Every 10 degrees, but we picked up a couple of them in between.
All right. Part of my philosophy in doing any experiment is that you must spend a little bit of time investing in the future. So out of this experiment, I wanted to take a few hours just to take a look at some kinds of data that we hadn't seen before to see what was there. I think that part of it that makes it so hard is that you have to decide when is the right time to do it. We started talking about doing this in the middle of the experiment, at a time when it looked like things were going to turn out and we were going to get finished with all of our data. And so at that point, it's kind of a gamble. You start to take this data when it's most convenient in the experiment, but you're taking a risk that you may not finish what you set out to do.
Although fewer points were measured than planned, enough data were collected for a successful run.
I see. It just comes naturally.
After 96 hours, their time is now gone.
Okay.
Tired, but also relieved, Jim and Carl are ready to leave for home.
I'm going home. All right. Well,
With the data collected, now begins the creative phase, in which the researchers will try to make sense of what the machinery has supplied.
I think it's also important to realize that there is an artistic side to the doing of physics, and that in fact the works that we create, the papers that we write, are just for us the same thing as, say, a picture to an artist, or say a piece of music to a composer. These are the results of our labors. This is where our imagination has gone. This is where our creativity has gone.
While Ed prepares graphs for the lunch meeting, Chuck breaks down the equipment so the next team can set up.
What I'd like to talk about today is the experiment that we completed over the weekend looking at the large angle J dependence and DP reactions. Besides myself, there were 3 other people involved in this experiment: Chuck Foster, Carl Pitts, and Jim Sowinski. The first set of data that we have here comes from the J equals L plus 1/2 transition to the state at 320 kilovolts. This state has large positive analyzing power.
This is also an important part of the physics process, sharing findings and ideas with others. The results Ed presents are tentative, but they do provide a basis for the analysis to follow.
We seem to get more positive results than what's given to us theoretically. If it turns out that that's true, then a deuteron which begins here as spin up, winds up having a proton and a neutron here, both of whom have spin down. So it's possible with some further calculations that we could come to understand whether or not the effect of the deuteron d state is important in these large momentum transfer reactions. Are there any questions? When we started out on this experiment, we had the idea that there was going to be a large dependence on the spin of the deuteron as it came in before the reaction took place. The theory was showing us something different. It said that it would depend mainly on what kind of orbit was formed. The way things actually turned out is that we got some sort of a mix of the two things. It first of all started to follow the theory, and then later on departed from it in exactly the way that we thought it would in the very beginning. The other thing that we were expecting was that we would probably see something new. So that's why we went ahead and at least took a little bit of data on the tensor analyzing powers, something we had not intended to measure in the original experiment. And that turned out to be very interesting because some of the effects that we were losing in the data that we were taking were reappearing over there, something that nobody had even thought would happen before.
In experimental physics, the process is as important as anything. In fact, usually at the end of an experiment, when the analysis is all done, you have some understanding, more or less, and a lot of questions. And those questions become the basis for the next round of experiments.
I hope this works.
Me too. What's the word?
Magic. Are you on magic?
I sure am.
I thought it was what you were writing.
Okay, Alan. Tell you what we're going to do. Let's develop this thing, all right? See if I can hold it back here in the candle flame, and we can get our message out of it. Okay. It's supposed to be here somewhere. Ah, there's part of it.
We're burning it.
Let's go over and take a look at this part. See? All right. See, and there's our message. Everything is new. Everything is different. You're one of the very first explorers to go there. You're seeing things for the very first time that no one has ever seen. To me, that is part of the thrill of doing physics, of doing any kind of science, is to explore that land for the first time.